In this part of our lecture, we are going to focus on how we can formulate the optimal control problems. Basically, there are three main components that you need in order to form a proper optimal control problem. And these components could be named as the objective function, a mathematical model, and the constraints. And we are going to, I'm going to explain this in detail to you. So basically, objective function defines what you would like to optimize. So this means what you would like to maximize or minimize at the end of the day. For example, in the previous lecture, we have given a motivational example, and at that one, the yield rate was our in focus. And this means that we were aiming to maximize the yield rate at the final time, which is TF. For example, the first objective function that we can use depends on the specific value at a specific time, which is the final time. And it could be written as like that. For example, minimize with respect to the control value u function of states at the final time. In this one, as you can see, the objective function directly depends on a value of a function at the final TF, and it doesn't consider what's happening in between from t is equal to 0 until t is equal to f. It only considers the final value of a certain thing. For example, in this one, in the previous one, it was yield rate. And this is named as Meyer form. But of course, this is not the only thing that we can use. We could also consider the trajectory performance in between. For example, how this yield rate ends up in the TF. So that may also be important. It's because of that we need another metric here. We need another type of objective function that basically sums every value or every quantity in between. And this could be written as minimize u from t is equal to 0, the initial time value, to the final time value, TF, and a certain criteria, L, T, X, and UT, and DT. So, the main difference of this one, as you can see, we have a cumulative sum in between. So, and we are now considering the whole time frame from the initial time t0 to the final time tf. But the missing thing here is that we are not considering the exact value at the final time like it was did in the Meyer form. And this type of formulation is named as the Lagrange form. And of course, intuitively, you can say that why not to combine these two and provide a more extensive type. And you are totally right on this. We can also do that, and it looks something like that. Okay, it looks like this. It's basically the combination of the Meyer form and the Lagrange form, and now we have an objective function that considers both the value at the final TF time and how this curve end up in this specific value. So this also, let's say, punishes the tracking performance with this integral here. And this form is named as the Bolzan form. And of course, there are some additions that you can make to this. As you can see, the integral part and the terminal cost function here is equally weighted. So this means that, for example, if this terminal value is more important for you, you can add some additional terms like, for example, let's say that this integral part is multiplied with VW and this terminal cost is multiplied with W2. So this means that by adjusting the value of the W1 and W2, you can provide the information that this integral part is more important for me or this terminal cost is more important for me. The ratio of W1 and W2, let's say, creates the difference in this case. Okay, so this is more or less all regarding with objective function. Then the other thing that you need in order to form an optimal control problem is the mathematical model, because your states will change with respect to the, let's say, dynamic system that you are dealing with. So like in the previous case, there is a chemical reaction, and basically you need to define that how this chemical reaction happens. In terms of mathematical tools, we have several options here. For example, one of them could be named as a linear system, and linear systems we can write as x dot is equal to a times x plus b times u, and y is equal to c times x plus d times u. Here we have defined a linear system, but of course this is not the only thing that you can use. For example, nonlinear ordinary differential equations can also be used, and they can be, let's say, written down something like that. So here you can see we have an initial condition, and we have a nonlinear function that defines the characteristics how my states are evolving in time. And of course, in addition to this, you can also write down algebraic equations if your system is compliant with this kind of mathematical formulation. Then this brings us to the final point, which is the constraints and bounds. So this is also quite important aspect, because we don't have, let's say, infinite resources. So we need to bound our certain control input values. So there's a boundary that we can apply. For example, I couldn't flow a volume which is greater than some certain value to my system, or I couldn't provide an energy which is greater than a certain threshold or so. And in the case of optimal control, these should be formed as constraints to our control problem. The final thing that I would like to mention in terms of formulation of optimal control problems is the constraints and the bound. And there are basically, again, three subtypes here, which is the point and terminal or endpoint constraints, the path constraints, and isoperimetric constraints. So point and terminal constraint, as it sounds, let's say, constrains some certain values at specific time value or at the final time. For example, so this is less than 0, but of course it could be anything, equality or and so on. So this is a point constraint because Tc is a time value in between T0 and the T final. If this Tc becomes as Tf, which is the final time, this also shows itself as the endpoint constraint, like, for example, again, the same one. And here I should also note that the Tc is somehow in between T0 and Tf. So as you can see, this constrains some certain value at some specific time frame. But of course, we can also define a path constraint. So this means that we are restricting how this value evolves in time. And this could be written as a function of, again, the values that we would like to restrict, which is, let's say, states at this time, control input ut, and they are most of the time function of time. And this case, t is again between t0 and tf. Yeah, maybe before proceeding with the isoperimetric, so I can give an example for the path constraint, and most of the time they are valid for input values. For example, we have a lower value for input, and we want our ut to be in between this lower value and the maximum value, u max, let's say. Okay. Or if we have a flow rate and if we have a constraint, we can also define something like that as a kind of path constraint. So, and this brings us to the final point, which is the isoperimetric constraints. And there's quite an analogy between the isoperimetric constraints and the Lagrange form here. So this was in the objective function, but we can also use the same notation in terms of constraints. And this can be written as like that, from t0 to tf, initial time to final time. Another function, this time h with respect to the x, and u, of course, is less than, let's say, a value c. How we can give an example for this? For example, we are feeding a chemical reaction, and let's say the reactor has a certain volume, and we don't want this certain volume to be exceeded. And in this case, we can formulate a thing like that. For example, let's say from T is equal to 0 to Tf, and feed is less than V max. So this can be considered as a constraint in this case. So this basically completes the subcomponents of formulating an optimal control problem. But in the next slides, I'm going to explain you how this looks like over an example case that includes basically all of these subcomponents. In this slide, I would like to briefly summarize what we have taught you previously over a generic example. So basically, you see all the things that I have introduced previously here. The first one stands as an objective function, or sometimes this is also named as the performance index. And since we have the terminal and the integral constraints combined, this is in Boltzmann form in this case. And we have the mathematical system formulation and its bounds here. Let's say mathematical model and its bounds. And here we have a terminal constraint here. And this one is isoperimetric constraints. And the last one is the path constraints for the input signal U2. And this could also be named as the control bounds in this case. As you can see, we are formulating our problem. This is what we would like to optimize. In this case, this is what we would like to minimize. And of course, in order to do that, we have some structural bonds. And the first structural bond is the system that we are working, and it shows itself in the form of mathematical formulation here. And of course, our system or structural components has some bonds, and this shows itself as the terminal constraints here, or is a parametric constraints, and the control bonds. So I would like to note here that not every single time you need a terminal constraint or so, or is a parametric constraint. So this is case specific, and this is strongly related with the type of problem that you are dealing with. But this one here proposes a general formulation for an optimal control problem. And in this part of our lecture, I would try to introduce you how we can formulate these kind of problems. And in the next one, hopefully, we are going to discuss in detail how these type of problems can be solved.